Here we go to the last part of the nervous system. We're going to be talking specifically now about how a signal is sent from one neuron to the next. Okay, so we're pretty much looking at this little spot right here, this spot right here. How the signal moves from here, jumps across to the next neuron. This is called synaptic transmission. Okay, this is the only real aim for today, only aim for this video. So a lot of people don't understand why we care about this. So I'm going to give you a real life scenario so that it makes sense. Okay? We have here an MMA fighter, okay? He gets punched right in the arm by this random guy in the street, okay? And we're going to see now what happens with his nervous system. So first of all, you get punched. What's the first thing you notice? You notice that you feel pain. So what allowed you to feel that pain? It's all about your nervous system. So for example, when you get punched, a neuron in your skin will pick up that something touched you, and it's going to send it to your central nervous system first. So here. And then this signal is going to be transferred to another neuron, which will take that signal further to your brain. So just right there, that's one example already of why we care about synaptic transmission, how the signal is sent from one neuron to the next. Now, furthermore, by the way, this is a sensory neuron, the one picking up the signal, and then a relay neuron is the one sending it to your brain. Now, let me show you another example. So now he understands he has been punched and he's feeling pain, right? His brain created this feeling of pain now. But now, that's not it, right? He wants to continue, he wants to respond. So this neuron will take a signal from his brain. His brain may have decided now to punch, not run away, because he's a fighter, he ain't gonna run away. So his brain decided to make the conscious decision and send a signal down to a neuron, so this one, called a motor neuron. So now here, this relay neuron will have the signal and it will get transferred now not to the sensory neuron, because that one feels stuff, but rather to this motor neuron that will send a signal to his muscles to punch or respond. So that's another example of why we care about synaptic transmission, how the signal is sent from one neuron to the next. Okay? So remember now, real quick, this signal I'm talking about is essentially a positive charge. Your muscle needs a positive charge to contract, a positive charge to make a movement. So when this guy makes the decision to punch this guy, he sends this positive charge down the neuron, because normally the neuron is negatively charged. So the neuron won't do anything under resting conditions. But when you think and make a decision, it sends this positive charge. But how does it get to the next neuron? By synaptic transmission, right? Okay, so that's what I mean. So let's get to it. In the previous video, we talked about how, let's say these are the two neurons that I just mentioned here, the one coming from his brain and the one going to his muscle, okay? So one coming from his brain. So he made the decision to make this positive charge. It is sent throughout the neuron and now it ends up here. In the previous video, we described what happens inside this neuron and how this signal gets sent throughout the neuron. See, throughout the neuron. But now we care about how it goes from the end of the neuron to the next neuron, right? Because if we understand this part, we know how the brain sends a signal entirely from the brain to the muscle. So let's get to it. So here we have it, synaptic transmission. So we're essentially zooming into this little part here, okay? This image here is zooming into this part. We've got the neuron, the end of the dendrite, because these are called these are called the terminal neuron, right? It's the terminal tail of this neuron, the presynaptic neuron. So it's basically the edge of it, the little ball. And then this here is the dendrite of the next neuron, okay? So what happens is we know a positive signal gets sent. But wait, before we do that, I need to label some stuff. So this right here, this membrane here is called the presynaptic membrane. And then, so this one's called the pre, because it's before, it's the neuron before the second neuron. So the presynaptic. Why synaptic? Synaptic, a synapse is basically the space in between the two neurons. So this is a synapse. Okay, so we call this the synaptic cleft or the synapse. They're both the same thing, synapse or synaptic cleft. So we call this the presynaptic membrane because it is before the synapse. So presynaptic membrane. And then this is called the postsynaptic membrane because it is after the synapse. Okay. Basically, in the end of a neuron, so here, in the terminal branches, here, we've got a little knob like this, and it has a bunch of vesicles in. These are little vesicles, little like sacs, okay? Vesicle, it moves stuff around. So you can think of it like a vehicle, a vehicle. It moves things around. Now this vehicle or vesicle has some things in it called neurotransmitters. Okay, these little red dots, okay? These little red molecules, they're called neurotransmitters. This makes sense. You'll see why soon, because neuro means brain, transmitters means things that allow a signal to be sent. They allow a signal to be transmitted. So we need these things to transmit the signal, okay? And it will make sense just now. Now, the specific one we're going to be talking about in this video is acetylcholine. So acetylcholine is basically an example of a neurotransmitter. You can have other examples like norepinephrine or stuff like that, but in this video we only care about acetylcholine. So these in here are neurotransmitters, and specifically in this video we talk about acetylcholine. Okay, now we have enough to go into explaining how this works. So basically what happens is we know that in the previous video, we saw how this positive signal is sent throughout the neuron and eventually reaches the end. So we know it's around here now. Now, basically, this positive signal is super important to be able to allow synaptic transmission to happen because we basically have these little channels, okay, at the end, at the terminal branches, okay, just like this. Oops. These channels can allow calcium to come in. But these channels normally are not open, okay? Normally the neuron is negative, as I mentioned, and so these channels are closed. But this positive charge essentially triggers these channels to open, okay? So when these channels open, calcium can just flow right in, okay? These little blue smiley faces are calcium, so they can just flow right in real easily, okay? So the positive charge triggered these channels to open, calcium flows in, okay? What's the purpose of that? So normally these vesicles that has these neurotransmitters in, they can't do anything. They need calcium to work. So when calcium comes in, calcium essentially goes and drags them towards this presynaptic membrane, okay? So eventually, in the presence of calcium, these vesicles can come to this membrane and fuse. And when they fuse, they can do exocytosis. So exocytosis is the process by which a vesicle can essentially release its contents outside through the membrane. So it fuses with the membrane to release this contents. And we know these contents are a neurotransmitter, specifically acetylcholine, okay? So now what we did was we had an electrical signal, a positive charge, allow us to release a chemical, okay? So we transferred this positive signal into a chemical signal, okay? So you can see the positive signal was important for inside the neuron, but to be able to transmit it, we need a chemical. So this chemical is released into the synaptic space. Now, what's it gonna do? So what it does is we have on the postsynaptic membrane this channel or this kind of receptor, okay? And this channel or this receptor has a little spot waiting for acetylcholine to bind or a neurotransmitter to bind. But normally it is closed. As you can see, it has a little barrier. So right now, nothing can pass. Now, we don't want acetylcholine to go inside. Acetylcholine, or this neurotransmitter, is only important to bind, okay, to bind to the little gap, to the little receptor there. Let me show you. So essentially, it will go like this, it will move and it will bind, okay? And once it binds, what happens is, now this receptor can open, okay? Whoop, it's open. Now, it's not open for acetylcholine. This receptor is specific for sodium. So, in this space all along, we had sodium, but sodium, oh crap. But sodium couldn't enter because it was closed, okay? So, all along we had sodium. But sodium couldn't enter as the receptors were closed, or this channel was closed. But in the presence of this neurotransmitter, it opens. So now sodium can go in, it can diffuse in. And what do we call this? We call this depolarization. So remember in the previous video, we showed that when sodium flows into the neuron, it causes depolarization. Okay, so we got them all flowed in, and now the membrane, the postsynaptic neuron, is depolarized. So this triggers, and we know when it's depolarized, that means since it has a positive charge, Na plus has a positive charge, it made this one positive now. And now the whole positive charge can continue to spread by this mechanism we described in the previous video. So you see, essentially synaptic transmission is the process by which we turn a positive signal, so a positive charge, and transfer it to the next neuron using chemicals, using neurotransmitters, okay? So it's pretty much, it's a combination of using electricity and chemicals to make the next neuron positive, okay? So it's pretty simple, right? Now there's a couple things more that you need to know, including what acetylcholine esterase is. So acetylcholine esterase is an enzyme, and we know that because it ends in ase. Anything that ends in ase is an enzyme. An enzyme is something that makes a reaction happen, right? So in this case, what reaction does this enzyme want to do? So it behaves like a scissor, okay? And we can see in the name acetylcholine, and we know this is acetylcholine. So acetylcholine esterase is an enzyme that breaks down or recycles acetylcholine, because we don't want acetylcholine to stay in the synapse forever. Otherwise, your muscles will get excessively activated, and that means you're basically going to spasm. Okay, that means the signal will continuously be sent, and this neuron will continuously be activated, and your muscle will continuously spasm. So we don't want acetylcholine to continuously be in the synapse. We want to recycle it. So acetylcholine esterase will be there to make sure that we chop them up, and move them back into this presynaptic neuron to be put into vesicles again and be stored until the next signal is sent so they can be released, okay? So that's all that acetylcholine esterase is. It's just like a recycler to make sure that this doesn't build up for too long. All right, so that's it. That's it. Now, oh yeah, by the way, I was just missing this. I just forgot to put it in, but this was to show that the inside was positive, okay? And now we know that after the signal is sent, this little machine will now measure a positive charge, okay? Now, last thing, so here is the word form. So I know I don't have any descriptions here, but here is the word form of exactly what happens. Okay, what happens in here, just in case you wanted to clearly read it. Now, the last thing you guys need to know is that there are some drugs and things that we can take as people to affect what's going on here, because I just described the natural process, but there are some drugs that can stimulate it or inhibit it. So drugs that can stimulate it. So I made a green line here to show that it stimulates it. So drugs that can stimulate this process, meaning increase it, include amphetamines, cocaine, or nicotine. Basically, this makes sense because we know nicotine makes you feel apparently happy or more. That's why people take it, because it makes them feel happier, right? So what it does is it increases this transmission, making you feel less depressed. So you're thinking more, you have more activity in your brain. Same with cocaine. When you take cocaine, you're going to be hyperactive because it speeds up this transmission, meaning your brain makes many decisions quickly, and you're actively awake. You're very aware. Okay. Same with amphetamine. So even people at work sometimes who work long hours take amphetamines because it makes your brain active. It makes these transmissions, the synaptic transmission, faster, so you can think more clearly, more fast. Now, there are some ones that inhibit it, and these include alcohol, benzodiazepines, cannabis, so weed, and neonicotinoids. These are just insecticides, basically. So this makes sense because we know when you drink excessive alcohol, you start becoming depressed. So your brain starts shutting down a little bit. You can't think logically. You can't walk straight. And that's because these neurons are inhibited, meaning you can't make decisions properly. You can't send signals effectively. So you don't make the right decisions and you can't control your body properly. That's why too much alcohol is bad. Same with weed. So weed will make you unaware of what's happening. You'll be a bit lost. You can't walk properly. You can't move properly. Okay, so these essentially have a similar effect. Now, benzodiazepines is a medicine used to help people be calm. So sometimes people have an overactive mind, and they have anxiety. Basically, if you have anxiety, you have an overactive mind. You're stressing out too much. Then doctors will give you benzodiazepines because these reduce this transmission, making you calm down. It can even make you sleep if you give enough of these, because then your mind is really inactive to the point where you fall asleep. Now, this one, neonicotinoids, are basically insecticides that are given and sprayed on plants to inhibit bugs from eating them, because these will go into the brains of the bugs and inhibit this transmission very badly so that they die, so that the bug dies, because the signals can't be sent to allow them to live. Like, it's inhibited so badly that nothing can happen in your body. You can't breathe, you can't eat. Whereas these are very vague. They do it a little bit to the point where you feel better or feel more relaxed. Whereas these do it really badly to the point where the insects die. So essentially, this is bad to an extent. It's an ingredient in pesticides, but it's bad to the extent that people stop using it because it kills unnecessary animals like bees and things that get into contact with it, that get into contact with the plants. Now, so I made it seem like nicotine, cocaine, and amphetamines are really good. It makes you stay awake and hyperactive, happier. But the problem with these is when you take them, you feel better. And so that means you're going to depend on it, because now if you stop taking them, you feel like crap. So you're going to feel like you always need to take them. And the thing is, if you get addicted to these, they don't only have an effect on your brain, they can affect other organs. So they can cause damage to your organs, which can lead to problems in the long run. And we know when you're addicted to these, you always depend on them. And because of that, you have many other side effects and your brain doesn't function properly because you are not you anymore. So it leads to withdrawal symptoms and dependence and all these kinds of problems in the long run. But they are used in some cases in medicine when someone is in severe pain and things like that. So, but for recreational activities, it's not such a great idea, obviously. So that was it for this video. And I hope it made as much sense as possible. And this is really everything you need to know. I don't miss out on any details for what you need to know for the IB. So, yeah.